Hi students, welcome to another video on control systems. Of course, this is also a transformation of circuits. So before we start, you go through these initial slides. Of course, to understand this video, you should be knowing very basic electrical laws. You should know how what is a transfer function of a circuit. So you should be finding out poles and zeros from the transfer function, and you should be knowing what is the stability of a system in terms of closed loop position in the S-plane. What you need during this lecture is you should have a notebook, few pens of different color, more importantly turn off all your distractions, set aside at least 45 minutes to 1 hour time, so write down everything, and of course participate in some questionnaires. Fine. Uh, Let us start. Uh, Now, let me just start with how do we represent uh, an Opamp amplifier using control system? So let us consider this is minus, plus, and let me consider this as my input voltage. This is so and so. Let me ground this. So this is now R1, RF, V in, and this is V out. So this is what a non-inverting amplifier, of course. So all of us know this is the non-inverting inverting amplifier. So this non-inverting amplifier, so we know that V naught by V in happens to be 1 plus RF by R1, provided the open loop gain of this Opamp is very large. So this is with a large open loop gain. So this is the expression what we know from the very basics of Opamp amplifiers. So let us try to represent the same using a control system block diagram. So now I can represent this Opamp as a block with open loop gain A0. So this is an Opamp representation with so and so, and of course I'm having the input is applied here. So this is plus. Now this is my input voltage that I have applied, and this is V naught here, and I'll be applying to this. I'm just feeding the signal back to this. Suppose if you say this is some Vx, so what is the voltage Vx you can think of? Vx is nothing but voltage at this point with respect to due to this V naught. So can I just rewrite this circuit as something like this? So this I'm grounding it. So this is exactly, let me say it as A, B, C points. So this is A point, this is B point, this is C point. At C point I have a voltage V naught. So at B point I want to know what is the voltage Vx. Between C and B I have RF. This is R1. So this is like a potential divider. This is like a potential divider. Can I write Vx is equal to V naught multiplied by R1 divided by R1 plus R2. R1 plus R2. Because this happens to be the current flowing in this circuit, and current multiplied by resistance is Vx. So now, so then what is what portion of output voltage is fed here? I can write Vx by V naught as equal to Vx by V naught is equal to So actually what is given is Vx is equal to V naught R1 by R1 plus R1 plus, so this is Rf, let me write it as Rf. So if I put this V naught here, so it will become like this. Vx by V naught is R1 by R1 plus Rf. Now the input to this feedback network, this is your feedback network. So what is the input to this feedback network? It is V naught. So now let me write that feedback network here. The input to that feedback network is V naught. What is the output? The output is Vx. So if you want to get Vx from V naught, what should be this? So this has to be R1 by R1 plus R. Correct? This is what I can represent this by this block diagram. What is A naught? A naught is the open loop gain of this, and you have a negative feedback coming here, and you are applying the input voltage through this non-inverting terminal. So now we know in control systems, suppose if you have, if this is G, if this is a feedback of H, if this is RFS, if this is CFS, if there is a negative feedback given, if this is plus. So what is CFS by RFS? CFS by RFS, which is nothing but the closed loop transfer function. Is this not equal to G by 1 plus G into H? This is a very well known closed loop transfer function for this block diagram. Can you just see these two block diagrams are identically same, where G is now replaced by A0, H is replaced by this R1 by R1 plus RF. So now in place of CFS you have V0, in place of RFS you have V. So I can write V0 of S by V in of S is nothing but, what is G you have? G is nothing but A0 divided by 1 plus A naught into what is this H? H is R1 by R1 plus RF. Correct? I can write it this way. So let us simplify this. I can take the LCM here. So it is A naught by R1 plus RF plus A naught into R1. This is now R1 plus RF. Correct? This I can write. So what I'll do now, so this I'll just group it like this. I will take out A naught as common here. So it is now A naught into R1 plus RF divided by A naught. I'll take it common. So then this will become R1 plus R1 plus RF divided by A naught. Correct? So then this will go off. This will go off. If A naught is very large, then this goes to 0. This goes to 0. So what you have? So ultimately you have an expression. I just write it here to keep it on the same page. So V naught of S by V in of S is nothing but R1 plus RF divided by R1. Correct? R1 plus 0. So it is R1. So if you further simplify this, will it not become 1 plus RF by R1? Is this not your closed loop transfer function of this non-inverting amplifier, which I can represent this entire block as AF. AF is, what is A naught? A naught is nothing but open loop gain of the op-amp, which is nothing but A naught. What is AF? AF is closed loop gain of the op-amp with input given at the non-inverting terminal. This is now AF. So can I now write this entire circuit? So can I write this circuit, which is nothing but you have minus plus. So this is V in, this is so and so, this is grounded, this is V0, this is now RF, R1. If this is A0, How can I write this as? This can be represented by a single block AF with input as V in, output as V naught. So what is this AF? AF is nothing but 1 plus RF by R. Of course, this is, suppose if you want to write Laplace, you can write this V naught of input is V in of S and its closed loop transfer function is 1 plus RF by R1. This is V naught. So this is so good. So we can able to represent a non-inverting amplifier by a single block which is AF whose value is 1 plus RF by R1. That's fine. So now let us consider a circuit now. Let me consider a circuit, something like this. This is V in. Let us consider this as RC. This also as RC. Let us take this as V0. This is V in. This is V in. So now if I want to find what is V0 of S by V in of S. V in of S. Again the transfer function of this particular circuit. So now let me first find its I can write it as, so this is now, so can I write this as R, this is 1 over SC, this is again R, this is 1 over SC, this is V0, this is V in of S, okay, V0 of S and V in of S. So now I can write this simply as some impedance Z1 of S and some impedance Z2 of S. What is Z1 of S? Z1 of S is nothing but R plus 1 over SC, which I can write it as 1 plus SRC by SC. Correct? It's as simple as that. This is Z1. What is Z2? Z2 is a parallel combination of R and C. I can write it as R into 1 over SC divided by R plus 1 over SC. So then what will happen to this? So this will become, that will cancel out. So what do you end up with? Do you end up with this R divided by 1 plus SRC? Correct? This is Z2. So now let me write, this is V0. Let me call this as this. This is V. So let me rewrite this, or let me just put it here. What is V0 is equal to, V0 of S is equal to IFS multiplied by VFS multiplied by Z2, which is nothing but R by 1 plus SRC. What is IFS? IFS is V in of S minus V0 of S whole divided by this 1 plus SRC by SC. This is what I have. So I can just continue with this. So what is this? So what is V0 now? V0 of S is equal to V in of S minus V0 of S multiplied by SC divided by 1 plus SRC, and this is multiplied by R by 1 plus SRC. Correct? It's as simple as that. So now can I just write this V0 of S into 1 plus SRC whole square is equal to V in of S minus of V0 of S into SRC. So what will happen to this? So I will take V0 of S as common factor. If I expand this, this will become a square RC whole square plus 2sRC plus 1, and this will also come there. It is again SRC is equal to SRC into V in of S, correct? V in of S. So naturally V naught of S by V in of S. So what will happen to V naught of S by V in of S? This will now become SRC divided by S square RC whole square plus 3sRC. So what is this? This is the transfer function of this circuit. This is RC, RC, this is V naught, this is V in. So for this circuit, I have this as the transfer function. So what we found is this can be represented by like this. Of course, this is represented by this. First it is by this, and then you can represent it as this, and this can be written as the transfer function of this circuit is this. So now let us combine both these. When I say both of these, let me consider this. So the circuit what I have now is this is minus, this is plus. I will have this R1 RF. This is RF. Let me call this as R1. This is that part. So this input, instead of giving the input as V in, I will take a fraction of this. You can see now what I have is this. This is now taken here. It's connected here, and then I have this. I'm grounding it. This is RC, RC. This V. Is it interesting? Can you see, am I having the same circuit here? The input is given here, output is taken here. To this circuit, this becomes the input, this becomes output. So this output goes as the input for your amplifier. So what we have now is, we have a special circuit which is something like this. This is minus, plus, you have a circuit. This is RC, and this is again RC. What is this? You have a resistor R1, you have a resistor RF. This is also wrong. Now, can we write a AC? Oh, can we write what is it? Control system block diagram for this one? So how can I replace this by? So can I able to replace this? What is this replaced by? See here, we can see, did we replace that by a single block here? Can I replace that entire thing by? So can I just replace this entire thing by AF? What is AF? AF is 1 plus RF bar. So what I'll do is, this circuit, I will replace it by something like this. This is AF. Now I have this signal. So now what is this? Now this is plus. This is plus. So what is given back here? So you are having a block now. What is this block? This is X block. So is this X? This is V naught of S. This is, assume that this is some V X of S. So what is the input given? Input is given here, output is taken here. So what I'm looking at is, what is VF X by V naught of S. Actually, V naught of S happens to be the input. You can see this is V naught. That is now the input. What is output? The one which is taken out here is this is output. So that's right. So and so. So is this not similar to this? So the input is given here. Now the input is given here. What the output? Output is taken. It is this. So can I write Vx of S by V naught of S as SRC divided by SRC whole square plus 3SRC plus 1 as my uh, suppose if you, of course, what is this? You don't have anything here. You don't have anything. Nothing extra is given here. So only this is going here. So is this something like this? You have a block without any input. You are looking at what is this? Correct? So what is this transfer function? Is this not equal to, suppose if I say this is V naught of S and suppose if you say this is V in of S. So V naught of S by V in of S, is this not equal to, this is what? This is now positive feedback. G by 1 minus G into H. Correct? In place of G, what you have? AF. In place of H, what you have? This is now entire H. This is H. This is H. So shall I write what is G? So G is AF, correct? Divide by 1 minus what is G? It's again AF. But what is this H? This H is SRC whole divided by SRC whole square plus 3SRC plus 1. Correct? Upon simplifying, can I write it as, so I'll take the LCM and take it onto this side. Is it not AF into SRC whole square plus 3SRC plus 1 divided by SRC whole square plus 3SRC plus 1 minus AFSRC. This is AFSRC. So can I further simplify and write the transfer function as AF into SRC whole square plus 3SRC plus 1 divided by SRC whole square. There is a 3SRC, there is a minus AFSRC. Can I write it as 3 minus AF into SRC plus 1? Correct? So now we know that this is a transfer function. This is a transfer function of this system. Of course, let us not give any input here. So it's actually V naught of S by V in of S. So let us for the timing, let us say it as V in of S. Now this is a transfer function. Where are the poles? The poles are at, of course, pole position. Pole position is nothing but roots of SRC whole square plus 3 minus AF into SRC plus 1 equal to 0. So what are the roots of this? You'll get it. So now we will consider an example. So let us take this as 1 kilo ohm. Let us take it as 1.5 kilo ohm. Let us take it as 1K. Let us take this as 1 microfarad. So this is also 1K. This is also 1 microfarad. Correct? So now let me find out what are this. So this is S. How much is R? This is 1K into 1 micro whole square plus 3 minus what is AF? AF is actually 1 plus RF by R1. So what will be this? So since you have this as, this is now 1 plus 1.5 by 1, which is now 2.5. Correct? So it is 3 minus 2.5. SRC is 1 milli. So it is 1K into 1 micro is 1 milli plus 1 equal to 0. So let me find the roots. What are the roots of this? So this is now a square into, so it is now, let me just, okay, let me find the roots of it. So it is 1 exponential of 3 into 1 exponential of minus 6 equals square of that is okay 1 uh, 1 micro plus, so how much is this? This is 0.5 milli, 0.5 milli s plus 1 equal to 0. So the uh, coefficient of s square is 1 micro, coefficient of s is 0.5 milli, and this is 1. So let me find out what it is now. So this is 1 exponential minus 6. What is b? 0.5 exponential minus 3. Then c is 1. Let me find the root. So root is uh, minus 250 and plus or minus j 968. So this is my root. So it's a complex root. So it is minus 250 plus or minus j 968 is the pole position. So where are the poles? The poles are on the imaginary, they are complex with their real value at minus 250, whereas its imaginary value is plus j 968, and this is minus j 968 point something. Fine. What is the system stability? We know that system will be stable if the poles are there on the left hand side of the spring. So you can see it is minus 250. This is your pole position. This is your pole position. So if you give a spike, if you give a spike as your input, so oscillations will actually, you'll get this type of oscillations. So this will end up with e power minus 250t sine 968t. So this is the response you're going to get. So with a gain of with AF is equal to 2.5, correct? With AF is equal to 2, AF is equal to 0.5. So what we'll do is we'll make RF is equal to 2K and R1 is equal to 1K. So can you see this AF will become 3 now? AF will become 3. When this becomes 3, can you see this is 3 minus 3, this will become 0. So now this term will become 0. What you will end up with? You will end up with S square. With AF is equal to 3, it will be S square 1 micro plus 0 plus 1 equal to 0 is my denominator of your CFS bar FS. So then what are the roots? What is this? So you have this as, okay fine, but this is 0 and this is 1. If you find the roots are, there is no okay real value is not at all there, but it is 0 plus or minus j 1000. So this is what the imaginary value that you have. So now where are the poles? The poles are on the imaginary axis at plus j 1000 and minus j 1000. Maybe you're all knowing that if poles are there on the imaginary axis, its Laplace inverse is sine omega t. What is this omega? This omega is nothing but this. So if you have poles sitting on the imaginary axis with its real term as 0, you will end up with sine 1000 t as the output, meaning that you will get a pure sine wave from this circuit if this value becomes 2 kilo. If this value becomes 2 kilo. If this becomes 2k, from this transfer function, from this pole position equation, this will become 0. The moment this becomes 0, the poles which were complex will come onto the imaginary axis. Once it comes out on the imaginary axis, the system started oscillating at a frequency of 1000. This is omega, this is 1000 radian per second. This is the frequency of oscillation. The frequency of oscillation 1000 this is coming from this RC, correct? This RC. So this RC will decide what is the oscillating frequency. That means the oscillating frequency is decided by this R and this C. When it will oscillate is decided by this R1 and RF. So this is Wayne bridge oscillator. So this is the analysis of Wayne bridge oscillator. So you might have seen that, or you might have already done an experiment. If the gain of the amplifier becomes equal to 3, or if the ratio of RF by R1 becomes 2, which is AF is equal to 1 plus 2 by 1. So then when AF becomes 3, then this circuit will give sine wave whose frequency is decided by this RC. So now if I actually give a equation, or if I give a circuit diagram, can you predict what is the frequency of oscillation? If I do it so, this is minus, this is plus, I will give, this is now 2 kilo ohm, assume that this is zero point 0.2 microfarad. Let me take this as 2 kilo ohm, because this should be R, this should be R, this should be C, this is also C, so it should be same values. 0.2 microfarad. If you make this as 10 kilo ohm, and if you make this as 20 kilo ohm, this is R1, this is RF, this is grounded. In such case, you will have the oscillating frequency omega in terms of radian per second would be equal to 1 over, so what will be the oscillating frequency? It will be 1 over 2k into 0.2 microfarad. So what is that? Can I just see what is that? It is 2 exponential of 3 into 0.2 exponential of minus 6 equals 1 over that is this. So this is 2500 radian per second. This omega is 2500 radian per second. So which is nothing but 2 pi f is equal to 2500 radian per second. Then f is equal to 2500 divided by 2 into pi, so many hertz. So many hertz, meaning that divide by 2 into pi. So you will have a sine wave of frequency 397.8 hertz, almost equal to 400 hertz. You will get oscillations, provided you are connecting 2 kilo ohm, 2 kilo ohm, this is 0.2 microfarad, 0.25 microfarad, and this frequency has, this ratio has to be 2. A ratio of RF by R1 2 will give a gain of 3, So the summary of this entire lecture is, we started from where? You can see our journey started very simply by starting with a non-inverting amplifier. How do we represent a non-inverting amplifier in terms of block diagram? We had G, then we have H, which is due to this RF and R1. We could able to represent this circuit in terms of a block diagram, which can be simply represented by a single block, which is AF. So which is this AF. So we could able to represent this by this, and then we took this RC network, a series here and then parallel. We try to understand what is the transfer function of this. So we could able to find out the transfer function of this is coming out to be something like this. So this is the transfer function. Then we started using this network and the non-inverting amplifier as this. Then we found out, okay, this is the circuit diagram. So then we try to connect these two as a block diagram. Then we are trying to simplify the overall transfer function without any input. Here you can see oscillator is one which gives a output voltage without giving any input. You can see even if you don't give the input, if the poles come onto the imaginary axis, so then you'll get the oscillations. So since it is positive feedback, it is G by 1 minus G into H. We substituted what is G, which is nothing but AF. What is H? It is the transfer function what we obtained for this, which is exactly this. This is actually HFS. This is your H. Then we wrote this. So then we are trying to simplify this, and we got this as our equation. So in this equation, we initially started by giving AF some 2.5. We found out the poles are complex, and which is going to give a oscillating and decaying output. That's what you are ending with. Uh, which will have this as your decay part, and this is your decaying expression. This is your oscillator expression, and we found out for AF is equal to 3 how it looks like. When AF is equal to 3, this S power 1 coefficient will become 0. You'll end up with this as your transfer function, sorry, the equation of the denominator, which is your pole equation, or we'll call it as characteristic equation. When you find the roots of it, so it was found that it is having 0 as the real value, but imagined value is plus or minus 1000, plus or minus j1000. So this is nothing but indication of system is oscillatory when the real part of the poles are 0. So the summary of this is, in a circuit, if you somehow make the poles to come onto the imaged axis, then system will start oscillating. For this circuit diagram, that will occur when AF is equal to 3. When AF is equal to 3, that coefficient of S will become 0. When this becomes 0, you will end up with poles coming onto the imaged axis. So where exactly they will come? So that is decided by this R, C, this R and C. So that's how a Wien bridge oscillator will work. On the same lines, we can able to prove. So I can able to write another circuit where a RC phase shift oscillator. So now you have again a similar type of Opamp circuit. It is now minus plus. Now we are considering an inverting amplifier. So this is your inverting amplifier. So this is RF, R1. So now something is fed back to this output. So where the output is fed back here. How it is fed back? It is fed back now. You have a network like this. So this is RC. This is now RC. There is one more RC. This are all grounded. This is R, 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 C, C, C. There is an input given, there is an output taken. You can find the transfer function of this. That network will going to sit here. So what is the network you have? So now this is the input. Now this output will become the input for your feedback network. This is V0. So you will have this and this. You will have this and this. You will have this and this. See, now this is going back here. C, 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 R, R, R. So now this is your AF, this is your H, this is your H. So we can find what is the condition, or will it work like an oscillator? Is it not? Is it possible to bring the poles onto the matched axis? We see. It's not only this is the only possibility. The other possibility is you can have a different network. Instead of having RC here, I can have this as my feedback circuit. Sorry, this is my capacitor, resistor, capacitor, resistor. This is now V in, V naught. So how do we use this circuit as a part of RC phase shift oscillator? This is RC phase shift oscillator. So now how do I realize this circuit? This circuit is realized using this. This is again R1, sorry, this is RF, this is R1. Now the feedback network has got a capacitor, a resistor, a capacitor, resistor, a capacitor, a resistor. All these are grounded, and this output will go here. This is grounded. This is so both of them are RC phase shift oscillator. Here this is phase lag. This is again grounded. Phase lead. Phase lead. So this is phase lag circuit. Again, both are phase shift oscillator, RC phase shift oscillator, but this is a phase lag network. This is a phase lead network. A phase lead network. So this is again CCC. This is R. We'll see the working of this circuit. Of course, here also we can find that when the gain is equal to minus 29, so then only it starts oscillating. The gain of this amplifier should be, of course, magnitude wise. If the gain is 29, then the poles will come onto the magnetic axis, then system is oscillating. We'll see that in the next video. Thank you.